Welcome to the fourth day of our conference. The first talk is in charge of Jesús Alberto Jaimes Arriaga with the talk The Powerfulness and Qualitativeness of Electron Density.
What I'm now going to present to you is part of my PhD thesis, which in general terms is intended to offer a metaphysical analysis of the quantum chemical knowledge. Well, I have structured the presentation as follows. I'm going to start by introducing the topic and setting my goal. Later, I will explain what electron density is and what is its role in the description of chemical system. Then I will discuss why Bader's interpretation of electron density involves attention about its nature, which is philosophically incoherent. Next, I will introduce the ontological nature of properties by focusing on the conception of properties as powerful qualities. After that, I will characterize electron density as quality and power and explain how this conception solves the Bader tension. Finally, I will give some conclusions. Well, quantum chemistry is a discipline where the traditions of chemistry, physics, and mathematics come together. Particularly, principles and laws from both molecular chemistry and quantum mechanics converge. And also, this science uses different types of reasoning, which is reflected in the diversity of theoretical schemes used to describe the same phenomenon. Even when these theoretical schemes are contradictory. If all quantum chemical theories are empirically consistent, how do we know which one gives us a better description of reality? To offer an answer to this question, we must deepen our level of inquiry, and the best approach to do this is the metaphysical one. In this way, the present work aims to elucidate the ontological nature of electron density, a central notion in quantum chemistry, and in particular, I will raise why Bader's view of electron density supposes an irreconcilable and counterintuitive metaphysical tension about its nature, while advancing my own proposal to better conceive the electron density in terms of the categorical dispositional distinction. Okay, the electron density is formally defined by this equation and contains all the relevant physical and chemical information of microscopic chemical systems, that is molecules, and the amplitude square of the wave function plays two distinct roles. On the one hand, according to Born's rule, this quantity corresponds to the probability density to detect the electron in a given region of space. On the other hand, by multiplying this quantity by the charge of the electron, Schrödinger interprets it as the electric charge density. It is common in textbooks to point out that it was Born and not Schrödinger who correctly understood the role of the amplitude square of the wave function. However, Schrödinger's proposal to understand this quantity as the electron charge density has not fully rejected, since it is very present in descriptions of atoms and molecules in quantum chemistry. I'm going to focus on Bader's view because, from my perspective, offers a robust theoretical framework to analyze the information contained in the electron density. Bader's view is based on the Schrödinger's interpretation, according to which the charge of the electron is not concentrated in one point. Sorry, I can. Sorry.
Podés tratar de dejar de compartir y volver a compartir. Ayer pasó algo parecido. Ahí está bien, ¿eh?
¿Está?
Sí, ahí cambió.
Bader's view is based on the Schrödinger interpretation, according to which the charge of the electron is not concentrated in one point, but is dispersed in the total space. proportional to the amplitude square of the wave function. In other words, electron density provides a physical model of matter, one in which point-like nuclei are embedded in a relatively diffuse spatial distribution of negative charge, the density of electron charge. Furthermore, electron density is a measurable property since it can be associated with a quantum observable and is routinely measured throughout X-ray experiments. According to Bader, a theory based on electron density provides the basis for a quantum definition of an atom in a molecule. The information contained in the electron density can be extracted through a topological analysis. This topology is defined in terms of the gradient vector field of electron density, which is constituted by a collection of gradient trajectories. These trajectories originate and end at points where the electron density gradient vector field disappears. These points are known as critical points and can be of four types. First, local maxima, which are associated with atomic nuclei. Second, two types of saddle points, one associated with bonding paths and the other with rings of bonded atoms. Finally, there may also be local minima corresponding to cages of bonded atoms. Through these topological characteristics, it is possible to recover the notion of molecular structure, a central concept in chemistry that gives molecules their identity. Another important factor is that the topology of the Laplacian of electron density can be almost faithfully mapped onto the electronic pairs of the Lewis model, a model that still dominates chemical thinking and is used to rationalize chemical reactivity. The Laplacian measures the extent to which electron density is locally concentrated or locally depleted. When the Laplacian is greater than 0, we have a local concentration of electron density. By the contrary, when the Laplacian is less than 0, the electron density will be locally depleted. In this context, it is established the Laplacian complementary principle. According to this principle, the zones of concentrated electron density of one molecule will tend to interact with the zones of depleted electron density of another molecule. It should be noted that both the topological characteristics of electron density and those of its Laplacian are specific features of each kind of molecule. Now, I would like to delve into Bader's interpretation of electron density. According to this author, electron density is the manifestation of matter in real three-dimensional space. Atoms and molecules are bounded objects that fill space. Therefore, they have shape, size, and solidity. This interpretation made by Bader suggests that electron density is a substance understood as kind of stuff. He means that electron density is the kind of stuff that molecules are made of. However, Bader insists that electron density is an observable quantity, unlike the wave function, since it is the expected value of an observable and therefore can be accurately measured. From this perspective, electron density will be a property and not an stuff. Nevertheless, the tension arises because the characterization of electron density as a stuff and as a property are not philosophically compatible. The electron density should be one or the other, but not both. Thus, I'm going to consider electron density as a property due to its observable nature. If electron density is a property, then the question is, what type of property is? To answer this question, let's turn to one of the central debates in property metaphysics, that about whether properties are categorical, qualitative, or dispositional. On this basis, we can distinguish two radically opposite positions. On the one hand, categoricalism that affirms that all properties are pure qualities without a causal role. On the other hand, categoricalism pan-dispositionalism that affirms, on the contrary, that all properties grant powers to the bearers. Orthodoxy dictates that qualitativeness and dispositionality are mutually exclusive attributes. What is dispositional is not qualitative, and what is qualitative is not dispositional. However, in recent years, several authors have proposed abandoning the categorical dispositional distinction, raising the idea that dispositionality and qualitativity are two sides of the same coin. Proponents of this position adhere to the identity theory, according to which a property is simultaneously qualitative and dispositional, where these are not aspects or attributes of the property, but the property's dispositionality is the property's qualitativity. This position is known as the theory of powerful qualities. I'm going to draw particularly on Intherson's view of powerful qualities. This author poses the following question. What is the particular nature, the unique essence of a particular property? According to the categoricalists, this unique essence corresponds to a quality, while for the dispositionalists, it is a dispositional essence. The problem is that to make coherent the idea that a property has a unique essence that is both dispositional and qualitative, it is necessary to think of the powers as intrinsic and not dependent on something external, as is the case of a property manifestation. On this basis, the author argues that the manifestations of a power are not constitutive of the nature of that power, but are merely epistemic devices to characterize powers. In this way, Interson proposes to conceive properties as ways of being whose unique essence is difficult to understand. But whatever that nature is, it is occurrently determined and makes a decisive difference in how the object behaves when partake in interactions with other objects. An example is the charge of the electron. Science describes the nature of charge in terms of what its bearer, the electron, can do. Even so, it is a property that is not intrinsically directed towards an outcome, and its heterogeneous behavior is not due to the heterogeneity of its nature, but rather to the heterogeneity of the interactions in which the bearer of the property can take part. Here, we should not understand the nature of a property in terms of behavior, but rather think the property as one that can give rise to behavior. In this way, Interson proposes to conceive the negative charge of an electron as a way of being that we cannot fully understand how it is in itself, but we can approach such an understanding by tracing what difference it makes to have such a property. Now, what about the electron density? The electron density of a given molecule contains specific information of that and only that kind of molecule. This information is analyzed in terms of the topology, where the specific features, i.e., the topological characteristics of the electron density of a kind of molecule become apparent. This is where the qualitativeness of electron density relies, since it reflects distinctive features that distinguish between kinds of molecules. Likewise, electron density determines how its bearer, the molecule, behaves when interacting with other objects. We are talking about causal interactions of the molecule at stake with other molecules or with scientific measuring apparatus. The dispositionality of electron density relies on this, since it determines the causal profile of the molecule. In this sense, I propose to conceive electron density as a way of being whose nature is difficult to understand how it is in itself, but we can approach such an understanding by tracing what difference it makes to have such a property in terms of giving rise to its particular behavior.
5 minutes, Jesus.
Thank you. Okay, well, by adopting this approach, it is possible to resolve the tension present in Bader's interpretation. Electron density is a property that allows us to understand the very nature of the molecule in terms of its behavior when it interacts with other objects. Through the topological characteristics of the electron density, it is possible to recover the idea of Bader that molecules have shape, size, and solidity. However, we must avoid attributing these features to molecules themselves. Rather, they should be understood as features of electron density. On the other hand, the observability of electron density is explained by its dispositionality. When a molecule is subjected to controlled causal interaction during a measurement experiment, we obtain certain effect as a product of the particular behavior of the molecule at stake. And this behavior was given rise by electron density. Finally, as conclusion, we have that the tension in Bader's view can be solved by conceiving electron density as a powerful quality. The theory of powerful qualities perfectly captures the multiple functions of electron density in the quantum chemical domain. This property is a powerful quality as it encodes information about what the molecule is, its qualitativeness, and what the molecule can do, its powerfulness. The qualitativity of electron density is shown in terms of its topology, while its dispositionality is manifested by its observable nature and its giving rise to behavior, the chemical reactivity. And that's all. Thank you.
Okay. Thank you, Jesus, for your talk. Now we have some minutes for questions. If somebody wants to make a question, please indicate in the chat, and then you can. Elena.
Hi. Just a quick question. I wonder how this focus on electron density affects our view on chemical bond, if it does. I mean.
Sorry. Could you repeat the question, please?
Yes. You stress the relationship between electron density, as far as I understand, you stress the relationship between electron density and molecular structure. So I wonder if talking about electron density and focusing on electron density affects somehow our view on chemical bonds.
Okay. Well, actually, there is some kind of relationship between the electron density and the molecular structure. However, in this case, I'm not focusing on how the electron density determines or defines the molecular structure, because from my point of view, the electron density captures some features of the electron density, but I think that is the electron density cannot be fully explained in terms of the electron density. I don't know if that responds.
Molecular structure cannot be explained fully in terms of
electron density. Exactly.
Okay, now we have another question from Klaus Rutenberg.
Yes, thank you, Jesus. I just have a question because I didn't understand what Beda was saying. I think you reported Beda as saying kind of the electron density is a kind of stuff molecules are made of. I simply do not understand what he means. Can you please explain that?
Yeah, sure. Well, the interpretation of Bader, in some sense, it seems to suggest that the electron density is a kind of substance, but substance in the sense of kind of stuff. For these reasons, at least from my point of view, Bader thinks that the electron density is the kind of stuff of which the molecules are made of. But it's a kind of the substance of the molecules. But this, well, at the same time, he thinks that the electron density is observable. For this reason, I found a tension between this interpretation of electron density in terms of the substance and in terms of the observability, because it will be a property. That's useful, Klaus?
I'm still not sure because I use the word stuff for substances, for chemical substances, and I don't understand how you can just so to say use the word, the notion of stuff for some things that are, so to say, referring to sub-microscopical pieces of matter. So I think it's really strange to use those words.
Can I add something? I think that it doesn't matter if it is microscopic or macroscopic. I think that he has in mind, Bader, a kind of matter dispersed all around the space with different densities, but a matter that fills all space. In this sense, is something material.
But I'm sorry, we have a sort of conference on the philosophy of chemistry here, no? And so and Beda always pretended or claimed to talk about chemistry, but I'm not sure whether he did it.
This is another problem.
Yeah, but why then talking about theories like Bada's theory, if it doesn't say any much more or any more than just normal, so to say, thinking about substances. This positionality you can just get to by thinking about substances. You don't need any calculations for that.
Well,
I'm sorry, I don't want to.
No, it's okay. It's okay. Thanks for the comment. I mean, I think that I need to think more about that.
Okay, there is another question from Sheriff Mata.
Yeah, thank you, Jesus. Let me turn off the other one here because I'm too people. So yeah, there is an echo. Yeah, thank you, Jesus, and I want to comment on Klaus's as well as Klaus's comment, and I don't fully agree with both of you actually, because I think because of the Hohenberg-Kohn theorem, the electron density carries by default all the properties of the system, and the electronic structure, the bonding structure has the signature within the electron density, as we all know, the one-path structure, for example, and the Laplacian that give you the lumps and the holes, and the literature. There is abundant literature out there that shows you the connection between bench chemistry and the quantum theory of atoms and molecules of Bader. And so I disagree with the view that the electron density does not carry sufficient information about the molecular structure. that first of all, you have to define what you mean by structure. And to my knowledge, there is never been anywhere in the history of chemistry since the time of the pioneers, you know, the old people, you know, that Kekulé and whatnot, the people in the 19th century, where they started to draw sticks between points to indicate chemical bonds. Nowhere in the literature has ever one been able to show a mapping or an isomorphism with these structures that you draw on paper, with something that you can really observe, whether by diffraction experiment or by calculation, such as the bond path. Yes, sometimes the bond path occur between atoms that wouldn't expect to have a link, but these are turned out to be the most interesting cases. It's taken as it was taken as a criticism of the theory, which is fine. Criticism is okay. Is needed actually. Is a healthy sign, but it turns out to be not founded criticism because, in general, because these cases where you have the non-classical bonding turned out to be the most interesting cases, and it led to all sorts of very various developments. So anyway, I'll stop here because I know the time is short.
No. Thank you for the comment. I think that it is true that the electron density of molecules determines many of the other observable properties of the system. And from my point of view, I think that we can approach the nature of the molecules throughout the electron density. However, the nature of the molecules is not, how do you say? I mean that only we can approach some nature, but not the fully nature of the molecules. In that sense, I think that the molecular structure cannot be fully understood in terms of the electron density, but we can approach some characteristics of that. I don't know if it is useful for you, Sheriff.
Is it an answer in principle or in practice? Because I think in principle it can, but in practice, no, because you don't know the functionals.
Okay, that's true. But even so, I think that it cannot in principle, neither in principle and neither in practice. I don't know. Well, maybe I need to think more my argument about that, but well, it's my position.
In principle, you have the Hohenberg-Kohn theorem.
Sorry?
In principle, you have the Hohenberg-Kohn theorem. The Hohenberg-Kohn theorem gives you the relationship between the electron density and any ground state property.
No, okay, but
in principle.
Okay. No, I think that well, the electron density is a good property to approach the molecular structure. However, you need more information of the molecule in order to identify the topological characteristics of the electron density with the molecular structure. If you don't have this that information, you cannot identify correctly these topological features with the molecular structure. In that sense, I think that I mean, if you only have the electron density, you cannot recover the the molecular structure.
Okay.
Maybe that's where we differ. But
continue discussing this issue in the coffee break. There is a time just for, we have 1 minute. Olympia, do you want to ask a question? Or?
Yeah, so it's a small comment about the Klaus comment. I mean, one thing is to ask for the relevance of electron density for molecular structure or in the field of quantum chemistry. And another question is the general program of quantum chemistry to reduce macroscopic chemistry. So I think that these are two different discussions, and you can, you can recognize the relevance of electronic density in a field of quantum chemistry, but being against to the general program, very strong reductionist program that tries to reduce macroscopic chemistry to chemical chemistry. And I think that this is this was the comment of Klaus. So I think that perhaps both are right, because they are talking about different levels. This is my small comment.
Okay, we are on time, so we will pass to the next talk.